So now that we have some experience with unit conversions, percentages, and working with proportions, we're going to revisit geometry a little bit in the context of relating all of the rules that we learned in geometry to these new types of problems that we've been looking at. So with this, you might want to refer back to area, volume, and all those pieces that we talked about before. So let's just go through some examples and we'll kind of relate the two ideas to each other. So in this first example, we have a 10-inch diameter pizza, and that requires 12 ounces of dough. And then how much dough is needed for a 14-inch pizza? So we have these two pizzas. We have a smaller pizza and a larger pizza. The smaller pizza has a 10-inch diameter, and the larger pizza has a 14-inch diameter. Now with the 10-inch, we know that the amount of dough required is 12 ounces. And then for the 14-inch, we don't know the dough required for the 14-inch pizza. Now, having these pieces of information starts hinting to me that we're going to do a proportions problem. How I can see that coming through is that I have diameter and ounces and diameter and unknown. So I have this relationship from this one scenario relating the 10-inch diameter with the 12 ounces of dough, and I have another scenario that's similar and should be proportional, but I have a missing piece. So we're going to set up a proportion problem. Now, a common mistake with this one is to use the diameter itself. So for example, making a proportion of 10-inch diameter to 12 ounces of dough. And where that causes issue is because that number 10 doesn't really bring through the idea of a circle at all. That 10 is just a distance. So with that, this amount of dough that's required isn't just based on the diameter. What we need to think about is that the amount of dough used is based on the area of the circle. So we're not going to use diameter. Instead, what we're going to do is use that 10-inch diameter, but we're going to make proportions based on the area of the circle, and then that'll be proportional to the amount of dough being used. And that brings through a more accurate relationship rather than just the distance across the circle. When we bring an area of the circle, which we'll just grab our formula, which is the area is pi r squared. Having that formula in there, we then know we have this circle at work. So, with that, we need our radius. So the radius is just half of the diameter, so we have this radius of 5, and we need this for our other pizza, which would have a radius of 7. So let's go ahead and set up our proportion. So what we're going to do is take the area of the first circle, so pi r squared, so that's pi times 5 squared, over, and then the amount of dough, which is 12 ounces. And that should equal, and we're going to take the area of our second circle, so pi r squared, pi times 7 squared, over, and then we don't know the amount of dough, so we can just choose a variable to work there. And then we just start simplifying. What I'm going to do is, as we go through this, I'm going to limit rounding in the middle of my work as much as possible. So I'm not going to multiply anything with pi yet. What I'm going to do is I'm going to keep this as 25 pi from that 5 squared divided by 12 equals 7 squared is 49 pi over x. And I'm just going to try to keep these as whole numbers as long as I can until I get to the very end. So when I have proportions equaling each other, or these ratios, we're going to cross multiply. So that 25 pi is going to equal x, or sorry, it's going to multiply with x. and then equals 12 times 49 pi. Now I'll go ahead to a calculator and multiply that 12 and 49. That'll be a nice whole number. So 12 times 49 is 588. And then I have pi at the end there. And now I'm going to divide both sides by 25 pi. Divide by 25 pi. And what we can see here is that the values of pi actually cancel out with each other. So pi is going to go away, which if we had multiplied and rounded before, we might have some error remaining when we do that division. So that's where we just want to be really careful of rounding too early, because doing all of these calculations, every calculation you do with a rounded number introduces more and more error. So all we need to do is have 588 divided by 25, and that should be a 23.52. So what did I solve for? Let's go back to our question. Realize this is the amount of dough needed for a 14-inch pizza. So let's put that together in a sentence. A 14-inch pizza needs 23.52 ounces of dough. All right. So when comparing shapes, keep in mind if the measurement they give you, is it better to relate the area rather than the distance, or maybe sometimes it's better to use the volume instead of the distance. Just be careful of that kind of trick to them. Okay, this question, I love looking at this question. So say you have a piece of paper and you want to make a cylinder with it. There's two ways to go about that. So the first way, let's call this way A, is to join the short sides. So if we have this 8.5 by 11, and typically how we see a piece of paper is 8.5 by 11, or 8.5 at the top, 11 along the side. So 11 is kind of the height of the rectangle, and 8.5 is the width. So what this would do is fold it around so that that 8.5 sides would be touching. So what this could look like is, and you can even try this out if you have a piece of paper laying around, this would be the case where it's going to be a pretty wide cylinder and not very tall. So these drawings will be kind of dramatic since 8.5 and 11 inches are fairly close, but it would be this case where you have your cylinder of paper and the sides that are touching are 8.5 inches. So that's one way we can fold the piece of paper. Another way, which we'll call method B, is to join the long sides together. So the 11-inch sides. So with this, if you fold the paper that way, gosh, you can probably hear me waving my arms around, and I know you can't see me, but if you touch those sides together, you're going to end up with this kind of long cylinder. So something that looks like this. And again, these drawings are way more dramatic than what's happening in real life, but gives us an idea of what we're seeing. So in this case, the sides that are touching are 11 inches. So what we want to do is compare the volumes of the two. And this is where you might think, well, the side lengths are the same, like it's all from the same piece of paper, the volumes will be the same, and I don't want to give anything away, but something kind of cool happens with this. So we want to compare the volumes of these two. So we're going to need the volume of the cylinder, and the volume of the cylinder is you take the circle, so pi r squared, and then you multiply it by the height of the cylinder to make it three-dimensional. So what we need is the radius for each of these circles that I'll just have them marked at the top there. So we have some radius there, we have some radius there. We know the height the height is given for each of these cases. So we have a height of 8.5 for one cylinder and a height of 11 for the other. So what we can think about is how this other side of the piece of paper is coming through. So in this scenario A, we know the 8.5 side is here. Well, the 11-inch side is along the outside of the circle there. So what that means is we know our circumference. We have a circumference of 11 inches for that case A. And similar with case B, that 8.5-inch side is along the outside of the circle, so that circumference is 8.5. So what we can do is, if we remember our formula for circumference, which is just 2 pi r, we take 2 times the radius times pi, what we could do is relate those two things together. In that, 2 pi r is going to equal 11. And then I can solve for radius. So if I divide both sides by 2 pi, divide by 2 pi, and I'm not going to round yet, like I was saying, just want to avoid error as long as possible. So the radius is going to be 11 over 2 pi. Same idea with case B, where the circumference is the same thing as 2 pi r, and we know the circumference in that case is 8.5. Divide both sides by 2 pi, and we have a radius of 8.5 over 2 pi. So, now I'm going to calculate volume. So for scenario A, our volume is going to come from the calculation of pi times r squared, which our radius is this 11 over 2 pi, and then we'll square that, times the height, which is 8.5. Now, let's look at how do we just plug that into a calculator. Let's not worry about order of operations and simplifying, because again, with these decimals, the more we use the decimals, the more error that gets in there. So let's look at plugging this in. So in the Desmos Scientific Calculator, I love this program for kind of organizing the work, and you can make the formula show up just like you wrote it on your piece of paper. So we have a nice pi button right here. So I'm going to plug in pi. I'm going to have parentheses and 11 divided by 2 pi. And then I'm going to close those parentheses. So you can just click to the right-hand side, or you can click the right arrow on your keyboard. I want to close parentheses and give that an exponent of 2. And then I want to multiply that all with 8.5. So that's giving me a volume of, and I'll go ahead and round this to 2 decimal places, let's say. So 81.85. 81.85, and this is cubic inches, so inches cubed. So there's our first volume. Now let's get the second volume. So I didn't leave myself much room over here, so I'm just going to draw a little line. Okay, volume. Similar setup, but our circumference, or sorry, our radius will be different. So the radius is 8.5 over 2 pi, and that'll be squared, and then times the height, which is 11. So I'm going to go back to the Desmos Scientific Calculator. What's nice is, okay, I could retype everything, and that's completely allowed. That'll be great. If you want to save 1 second of your time, we can just edit the formula that's in there. So where I have 11, I want to replace that with 8.5. Where I have 8.5, I want to replace that with 11. So just a little bit of editing, and we have our volume, which is very different, 63.24. So this is where it seems like they should have the same volume, but by using different side lengths, it does change the volume. So joining the shorter sides together will make for a larger volume, and we want to see by how much more. So we're just going to take the difference of the two. So if we just take 81.85 minus 63.24, we're going to see a difference of 18.61 cubic inches. So to put that together in a sentence, the cylinder joining the short sides together is larger, or let's kind of mimic their wording, would hold more. Together would hold more. In fact, would hold 18.61 cubic inches more than the other cylinder. Something like that. So we get our comparison, we see which one's larger, and by how much. Alright, one more example here. She'll deal with some geometry. So we have an air pump, and it takes 5 minutes to fill a twin-sized air mattress, which is 39 by 8.75 by 75 inches. And we want to see how long will it take to fill a queen-sized mattress, which is 60 by 8.75 by 80 inches. So, kind of like what happened with the pizza, we don't just want to use a side length here, or a height, or width, like width, height. What we want to do is the air is coming through as a volume, just like how the dough came through as an area. So, with that, we want to think about volume here. So we want to take comparing the volume of the air mattress to time. Again, with these ratios, you can switch. In fact, let's do that. I mean, it doesn't make a difference. That's kind of the point I'm making, is we could take the time compared to volume, or volume compared to time, and it'll be the same calculation. I'm just switching this up so that our unknown is in the numerator when we already have an example in this one with the unknown in the denominator. So, what we have is time. So, for the twin-sized mattress, we have 5 minutes compared to the volume. And this is going to be a rectangular prism. So what we would have for volume, where we have some width, length, height, volume is just the multiplication of those three values. So what I'll have in the denominator is just multiplying 39 times 8.75 times 75. And that's going to equal, and we don't know time for the queen size mattress, so that will be our unknown, over the volume of the queen size mattress, so 60 times 8.75 times 80. So then, solving however we need to, we can cross multiply. However, all we really need to do is get rid of this denominator here. Let me take one step to simplify a little bit further. So 39 times 8.75 times 75, that's going to simplify to 25,593.75. And then 60 times 8.75 times 80 is 42,000. So you can cross multiply and solve for x, but really we just need to move that 42,000 away from x. We like x in the numerator there. So what I could do is just multiply both sides of the equation by 42,000. What'll happen is on the right hand side, they'll just cancel out, so all we have is x. And then all I need to do is plug in this calculation on the left-hand side of my equation there. And with that, let's go to our calculator. So 42,000 times 5 divided by 25593.75. So we get an 8.21 if we round to 2 decimal places there. So, what did we find? We found an amount of time. This is in terms of minutes to fill that queen-sized mattress. So we can say it will take 8.21 minutes to fill a queen-sized mattress. Now, in terms of rounding, you could switch this to say like it'll take about 8 minutes. If you want to get real exact with it, what we could do is express this in terms of minutes and seconds. And so we have these 8 whole minutes. And a common mistake here that I want to go through is that often students will change this to 21 seconds. However, as we talked about in percentages, percentages are all about like out of 100, and this is like 21% right here. At 0.21 is 21 hundredths, but time is out of 60. So what we need to do is, instead of just changing that to 21 seconds, think of this as 21% of a minute, of 1 minute, or 21%, even better, of 60 seconds. So what that means is, to get seconds out, we would take 0.21 times 60, and that'll scale it so that then it's a measure of time. It's also like a unit conversion in a way. We have 0.21 of a minute, how many seconds is that? So with that, if we plug that into a calculator, it should be about 12.6 seconds. So if you get a decimal out with time, just be careful that the decimal portion is converted correctly to be out of 60 and not 100.